First, a few words to introduce myself. My name is Delphine Bugner. I work in BAM in Paris. It's a React Native agency specialized in mobile development. I do love Berlin. I studied German at school, but I won't try to do this presentation in German because it was a long time ago. It's been 3 years already since I'm using React Native, and I'm now working as a tech lead engineering in BAM. It's my first presentation in English, so be nice with me. And it's the first time I also present this topic, especially, so it's brand new content, I hope, for you. I hope you will learn some stuff. A quick introduction, like many developers' story, the story I will tell you tonight is a story about a bug I encountered when I was a very young React Native developer back in 2021, 6 months React Native years old. And this was a bug I had to deal with. The text here, hence, was going a little bit out of the screen. If you compare with the one I put in green, this is the correct displaying. So what did I do back in 2021? I asked Google. I found the exact Stack Overflow issue I was looking for, React Native text going off my screen, refusing to wrap, right to do. Issue seen not less as 400 and 1,000 times. And fortunately, it had an answer. Okay, you should add flex1 and flex wrap. Cool. Oh, there's also a commentary. Apparently, flex1 is enough. So what did I do? I copy-pasted the Stack Overflow answered, and it worked. This is a pull request I made. Now the text is perfectly wrapping. You can see the distance, the kilometers in the label. So cool, flex1 is working. Back in 2023, I would have asked probably ChatGPT, and ChatGPT got it right too. You must add flex1 if your text is going out of screen. Okay, but do I have to add flex1 to every component on the earth? And what do I speak to you about that tonight? Well, it's because it's one of the most common bugs I've ever seen on React Native. I've seen it on my every project. This, for example, is the health tech app I was working with last year. You see the burger menu is going out of screen. Or here, the Twitter icon is not supposed to be that close to the border of the screen, so the margin is not right. Or here, you can see the whole text for the event, still going out of screen. Or even this year, in 2023, the author name still going out of screen. Every time it's happening where there is a text in a row, a text near an icon, near an image. Either the icon or the text is going out of the screen. So this is my conclusion. It's really confusing. And the reason why it keeps happening, it's because the reason behind is not intuitive at all. Why do you need this flex1 parameter? And why was it coded like that in the first place? So I decided to dig up. First, I will explain to you why the fix is working. We can start with this. Maybe you know, but it's just a quick reminder on the flex algorithm. I used to think as a baby developer that we had to allow the text to grow vertically, to have more space and to wrap easily. But it's actually, yeah, the shrink parameters that plays a role. We have to allow the text to reduce its size to fit in a smaller container. This is in one of the examples I used. It reduced. We can see the burger menu fully. So this is why the fix worked. The shrink parameter controls the size of the element on the main axis of the flex direction, not the other way. And why was it overflowing in the first place? Well, in a row, elements never wraps. By default, flex wrap is set to no wrap in the React Native style. So when an element is too big, it just goes out of screen. But why was the text too big in the first place? That's the real question. Why do we have to adapt it? Do you know why? I hope not, because I'm going to answer it tonight. Well, 2 years ago, when I first tried to think about this bug, I found this answer. Text in a row always takes its parent size, always, ignoring the siblings around. Here, I used this ancestry technique of background colored red to debug my code. You can see you have the parent in red, and you have the text, and the overflow part is quite the missing part to reach the parent size. It becomes obvious if you reduce the parent to half of the screen only. You can see the text perfectly follows the parent, even if it has the place to expand virtually, because we are only half of the screen. So that was the conclusion. Text in a row always takes its parent size, so you have to add the flex shrink to force it to consider the icon near it. But I was like, why was it coded like that? Why do I have to do this? And it's the same on iOS and Android, and I see it's not written anywhere in my JavaScript, so it has to be behind. And behind means in the native part of React Native, and more especially in the yoga part. So this is what I'm going to talk about tonight. Yoga. What is yoga? You may know it already, but it's a quick reminder. Yoga, it's a layout engine used by React Native. What is a layout engine? And not engine. It's basically the tool you use that helps you convert a JSX and style sheet into boxes on screen. Everything on screen must have 4 values: a width, height, top and left position. So Yoga is here to give you the 4 values for absolutely everything in your React Native app. It was introduced by Christopher Shadow back in 2015. I recommend you to see the video where I explain it to people. It's really interesting. He explained that when working on React Native, they needed something to compute the size of element on screen, but what they had in the native APIs was really boilerplate and complicated to use, constraints and everything, mathematics. They didn't want to use that. What they wanted to use was Flexbox. Flexworks was the most famous thing on CSS, really easy to use, really straightforward. So they said, okay, we want to use it. Let's implement the algorithm in React Native for us. They did that in 2 weeks. They recorded the entire Flexbox algorithm in test-driven development that generated random nodes, random trees of node, and compared the result of width and height of their algorithm with the result of a classic browser. And by iterating like that, they quickly delivered a pretty good implementation of the Flex algorithm. It's quite remarkable. And then Meta open sourced 1 year after at the name of Yoga. I think Yoga was like, it's easy to use, it's like peaceful. So it's a pretty good name. Because it's really like React Native vibe. This learn once, write anywhere. You know the CSS, you can use it in React Native. But it's without the withdrawal of the CSS that are that. For example, the cascading part. Yoga is also very React as it's atomic. You write the style of your component in your component, and you don't have consequences on everything on the chain after. It was also one of their principles when they implemented it in 2015. It's written in C++, so it was designed like this to be really efficient. So it's part of the 25% of C++ we have in React Native right now. It's not the only part written in C++ with the new architecture. And Yoga is platform agnostic. It means that you don't have to, you can connect it actually to other platforms than React Native. For example, Litho is the library for Android using Yoga, or Component Kit, which is a library for iOS. In React Native, how does it work? well, as I said, everything starts with the GSX. You write your component and your style. From this, React generates a tree. In our case, the tree is quite simple. We only have one component, the app. Then, from this tree, using the bridge and asynchronous event if you use the old architecture, or using GSI synchronous if you use the new architecture, you create the same tree, but on the native side with native components. Here you have the root view, the raw container view, and then the icon and the text. It's my basic example I will use during the entire presentation. They are native components. For each one of them, you build what is called, in React Native called a shadow view. A shadow view is like a copy of your view. You have one for every node in your native tree, but you only give them the layout properties. For example, the shadow nodes don't have the color properties because you don't need color to lay out a box. So maybe it's why they are called shadow. They only have the dimensions of the style, not the colors. And from this shadow tree, you build the yoga tree. Again, you have a fourth tree with a yoga node for each shadow view you have. You give to them the style properties of your node, and you can also give to them a native measure function, as yoga is just an algorithm of layout resolution, but at the end of the day, the measure function are depending on the platform you're connecting yoga with. In our case, Android or iOS. But all the yoga node lives on the C++ side, on the background thread. So this is where yoga runs and generates all the width 8 top left for everything on screen. It gives it back to the native. The native added the color, the border styles, everything. And we have everything appearing on screen. Obviously, there are other stuff here. For example, you might have heard about the view flattening on Android happening here. Or there's also a specific dynamic when the tree is re-rendered instead of completely created with dirty nodes and optimizations. I won't talk about that. The part I'm interested with is this one, the C++ one. How do you go from a tree with style properties to width and 8 absolute position for everything on your screen? That was the mystery I wanted to solve. And where is it written in here? A text in a row always takes its parent size. This is what I call solving the Yoga Enigma. Okay, so going through the algorithm, how does it work? Well, there is this function called calculate layout, and you call it on the root node of your tree, and that's it. You're done. You don't have to call anything else. You have all the measurements. Thank you for tonight. No, obviously not, because, well, this is quite the function. It's more than 100 lines of code in C++ with a lot of condition, constant, naming, blah, blah, blah. And it's also calling itself. It's a recursive algorithm. So you don't know how it ends, because when you're a parent, you have to be measured, you have to measure your children, but when you're the children, you have to measure your parents to know how to be measured, so you don't know where does it start, what does it end. How are we? Oh, that's confusing. So let's take things quietly in our baby case with only 4 nodes, and on our baby app with only 3 components. And yeah, thanks Expo for the template. And then I connected it to Xcode, and I put like 100 breakpoints in the native code, in the C++ code actually, to see, okay, what are the values? Where is it computed? In my precise case, I won't try to cover everything a layout engine does, but in my case, and still trying to understand why the text is going off screen. So, are you ready? Okay, so as I said earlier, everything starts with the calculate layout applied to the root node. Okay, we call it, obviously with the node from the native, we also call it the calculate layout function with available width and available height, the context in which we are measuring. So initially, we just give it basically the device dimension. This is where everything starts. And we also call it with what is called the measure mode, which is saying, how do I have to measure this node in the context? Yoga, there's only two ways to measure an element, and two only. Yoga call them this way. There is the undefined way. It's when you have an element, you don't know how it fits to its context, so you just stick to what's inside you, basically. It's like content-driven mode. And you have the opposite. Do not care about your content. Just follow your parent, follow the constraint around you. It's what Yoga calls the exactly mode. It's also the mode that is used when your widths or heights are fixed in your style. You exactly follow your widths and heights. This is how you're measured, you're done. And actually there's a third way of measuring things in Yoga, which is called the utmost mode, which can be either the undefined mode. If the content is smaller than the parent, then you have to stick to the content. But if the content starts to overflow the screen, then you're restrained to the parent. Typically, the utmost mode is used for the text. When a text only has a few words, the text container sticks to what's inside. As soon as your text is longer on several lines, its width is the one from the parent, because the text always wraps in React Native. In the undefined mode, for example, if you had a text in a scroll view horizontal, for example, you would have only one long line. You stick to the content only. And in the exactly mode, even with a short text, you could stick to the parents, as if you put a flex grow on it, for example. So those are the three constants that are used absolutely everywhere in the Yoga algorithm. Okay, so in our case, we used the exactly mode because the roots node had the flexed one to take all the space on screen, so you exactly fit to the device dimension. And we can start the computation. Now we know the parameters we're using. Yeah. The developers that have made Yoga gently put step on it, step 1, step 2. We have 10 steps to solve the full algorithm. Step 1 is just collecting values. What are the flex direction? What are the padding? What are the margin? Reading them from the native side. Step 2 is compute the actual available side, because there is the one you receive from your parent, from the context, but you subtract the margin, padding, and border size of it. And you also check for the min-max constraint. And then, as soon as the step 3, you check if you have children. And if you have children, you have to stop. You have to, before computing your own size, you have to compute the size of your children. You have no choice. So this is where the recursion starts. So we have to stop our rows computation and go to our row container computation. So we recall calculate layouts with other arguments. We are still exactly for the width measurement because item have a stretched position by default in React Native. But the height measure mode is at most. At most because we adapt what's inside by default also. It's a flex type property by default. And we still have all the space we need. We don't have constraints on the code. At most because it's undefined, but we don't have a flow. We're not in a scroll view, so our content will always fit inside of the screen. But it's the same. So, unfortunately, we still have children, so we can't go further in the computation without actually measuring our children. So we start to compute the text. I don't know why the text. It happens here like this in Xcode. For the text, width measurement it's like the parent. It's the utmost way. No, sorry, the 8 is like the parent. And the width, because we are in a row, it's the same. In a row, you don't know in advance the width you have. You look at your content to know your size exactly. But for the text, we have a difference compared to the others. Before checking the children, Yoga does something else first. It checks if you have a measure function attached. Remember the native function we attached when we created the Yoga tree initially. If it has the measure function, the algorithm just stops. Okay, now I know how to measure this node. You don't have to go further. You don't have to go anything else. You just have to apply the measure function you received from the native side, and you're done. So this is what we do for the text node. Yeah, this is the return. Almost hit 100 lines before the actual return of the function. We have these parameters coming from Yoga, and we go back to the native, asking to measure a text. This is the text shadow view. The function is here. Basically, it does 3 things: setting up a little cache system, and then on iOS, it initializes a UIKit container with the maximum size given by Yoga. It set also the max number of lines you could have set in your properties in React Native, or the adjust font size parameter you could also have set. It's interesting to see that Yoga doesn't care about adjust font size parameter. It just plays its role here in the native text shadow view. And then we call the UIKit useRect for text container function. I think the naming is pretty straightforward, but let's just draw it because you might have noticed I like drawings. What's happening? You draw a rectangle with a constraint you receive from Yoga. So we are still with the device dimension here because we still had no constraint above or below or whatsoever. You add the text inside, and the function returns to you the width of every line and the height of the complete text. So what are the values we return to Yoga? The values of the text width and height. The width is basically the width of the largest line, and the height, yeah, we just have 1. On Android, this function is static layout builder, but it's quite the same. You give it the text, you give it the constraint from Yoga, and it returns to you the measurements. And I have to warn you, those functions are extremely expensive to run. So it will be important after that. Yeah, but now we can go on in the algorithm, and so now the width we computed, yeah, 361. So I was wrong earlier when I said it always takes its parent size. No, it was built using a rectangle that has a parent size, but then after that, it's the width of the longest line inside of it, the final width of the text, given by the native. But we're happy. We have finally measured 1 node after 20 minutes. Cool. With the following numbers here. Alert. We measured the text with a too big container. So it might be the explanation. Maybe we will come back to it later. We don't know, but it will probably explain the bug later. Now we can start to compute the dimension of the icon. This is we can go quite quickly because the dimensions are fixed in style. It's just a 50-50 square. And because it's fixed in style, measure mode is exactly. So we don't have a measure function for this node. We check if we have children. We don't have. And it's a second way out of the calculate function algorithm when you have an empty container. Then you just take the measure you have and you exit it. OK, and now we just have to move up the tree. Once we have every children computed, you can go back to the container and following the full layout flow that we skipped for the children. It's the 10-step computation, collecting flex item into flex lines. We don't care. We don't have flex wrap. OK? Resolving flexible lengths on analysis. We don't care. We don't have flex factors on our children. Then there is an items computation. That's the first time we actually compute top and left parameters. So we don't have stretch items, but we have cos-axis alignment, so we will have to do this. Multi-line cell we don't have to do. Final dimension, finally, and absolute children we don't need. Okay. So we can just go from step 3 to step 7, where we center the children. And then step 9, we are still in the 8 at most, so we just have to compute the dimension from our children. And finally, we have the 8 of our raw container. That's basically the same as our text. I put you one screenshot of the actual code for this. The total line cross dim is the 72 we were looking for. And then we move up the tree again for the root container. It's the same. We can skip almost every steps of the algorithm, center the children, and both dimensions are exactly, so you fit to the parent. It's actually the easiest computation in all of the list I've made, because we just fit to the device dimension, but you can do that only if you're absolutely sure that you have measured all of your children. It's also your responsibility as root node to render everything else. And we are set. We have measured everything on screen. Congratulations to us. So it's time for a quick recap. We have the full measurements, cool. We also have seen the full calculate layout algorithm, which was one of my intentions to explain it to you at least one time. We know how to measure a text natively in React Native, and we know the bug origin. We measured the text with a 2-bit container, but we had no information at this step of the algorithm to compute it differently. Okay, the bug in detail, we have 50 plus 361, it's 411, it's bigger than, yeah, you can read it. Again, what happens with flex shrink in the algorithm? We do a second pass on the raw container. That's the moment where, when we were doing the second pass, even the first time, Yoga realized we were going out of screen. It computed the remaining free space, and the remaining free space was negative, which means that we were already going above the limit. But because it had total flex factors to 0, it quit the algorithm. By adding the flex shrink, we have a negative flex shrink scale factor, so it just means, okay, there's an if condition. We will have to go back to our children and resolve their lengths according to this factor now. This step is divided in 2. In CSS, it can take up to n steps, but in React Native, they simplified it. First, check the min and max constraints. We don't have, so we don't care. And then distribute the free space between the children. Our free space is negative, so it means we will have to reduce their size with these tiny computations, because when you have several that are able to shrink, you have to distribute between them. You know that, I think. But it's nice to see it actually doing by React Native. And you have the new child size smaller than the previous one. And we remeasure the text using the native function we talked about earlier. Still using the UI kit function, but with a new rectangle smaller than the previous one. And the final dimension, quite interestingly, because we are measuring in the exactly mode. Exactly means, flex means you use the exactly mode because you stick to what's around you instead of sticking what's inside of you. So the final dimension of the text will actually be the one from the container, not from the lines inside of it. And then we climb the tree as we did before. So I will go quite quickly on this. Okay, so you can compare the 2 results we have here. So now, I think time for a quick recap too. We have done the full flex algorithm, an example of how it is coded in Yoga, including when you have children that are able to adapt their size. And we have understood how the bug fix was working. You remeasure the text with a smaller container. We understand it so well that I was like, okay, but it's working like this in React Native, but how is it working in CSS? Because I don't think the bug is happening in CSS, and this is the main reason why every developer is confusing on React Native. So what's in normal CSS for normal people, not mobile people? And I did the test with exactly the same use case, raw container, icon, and text, without putting any flex shrink on the text. And the text was wrapping correctly. I was like, what? But how is it coded? So I tried to read the W3C conversion, and it's really interesting, but it's somehow even worse than the Yoga code. So I was doing some weird, crazy theory of, yeah, I must have invented something crazy in CSS. No, the answer is completely obvious. It was so obvious that I forgot it. By default on web, flex shrink equals 1. I forgot it. It's been such a long time since I'm a React Native developer. I forgot this basic CSS rule. So it's wrapping for the exact same reason as in our bug fix, because flex shrink equals 1. So the real question is, and yeah, flex shrink equals 0 by default is actually one of the 4 exceptions quoted by React Native for the layout with flexbox here, along the flex direction default to colon, because we use our mobile phone vertically, not horizontally. So the real question is, why this exception in Yoga? Why haven't they put flex shrink to 1 like in CSS? It would have been so much easier for everyone, and I wouldn't have had to do this talk. Well, because Yoga does this little arrangement with the CSS rules. It doesn't explain in the code why it does this for the flex shrink. It does this for another arrangement it's done. Remember the 3 measure mode I told you about? There's actually a 4th one in CSS, explained in the W3C theory, which is called min content size. And the min content size is the minimal size for a text, and it's the length of the widest word in the text. Quite interesting, I didn't know that. But if you try to reduce your navigator size, you will see that the text will shrink as long as it reaches the length of the longest word. It doesn't want to cut the word. And the Yoga developers put an explanation in their code to explain why they wasn't supporting this. They said, we don't support default main size because we don't want, because it's expensive. Calculating the minimum word is expensive, so main size is 0. Okay, still it's not our case of flex shrink, but the word has said, it's what I told you about the text measurements. It's what is expensive, and the whole Yoga ecosystem is built to minimize the number of times you have to actually measure a text. If you put a flex shrink 1 by default, you will have to measure every text at least twice. One time to have the flex basis size with a full size, and one second time, as we saw when we went through the algorithm, once you know everything on the line, to reduce its size. And sometimes, even on my bug, it's not only a text. Sometimes 2 texts are wrapped in a view, so you have to plug the flex shrink factors on the view. But still, it impacts, you have to measure twice the view, and so twice the text below it, and it can be even more nested. And you have seen how complex it is to visit all the nodes with all the algorithm all the time in the rendering time. So they have said, okay, we don't want this. We don't want to measure everything all the time. So we just decided to not use the flex shrink 1 by default. If the developers really want to use, to measure twice their text, they have to say it. They have to put the parameters in their code, because we won't do it for them because it's bad for performances reason. Okay. So this is a recap. So Yoga is a flex engine, but somehow flexing the rules. And the real culprits, they are here for the enigma we were trying to solve tonight. It's them. The useRect UI kit and static layout builder, basically, on the native side. And to conclude, because now we have solved the mystery, I can conclude my speak. I said to you that Yoga was agnostic, so it means you don't have to connect it especially to UIKit or Android's static layout builder. So they have a configuration called use web default inside of the code. It's a Boolean you can choose in your Yoga configuration, and nicely it resets the flexion factor to 1 everywhere in your code, along also doing the flex direction row by default when you don't use it. So this is the power of Yoga. If you want to connect it to another platform that is not performance consuming when it measures the text, just activate the use web default to 1, and no developer will get lost with burger menu going out of screen, just as I did. For the future, there's a whole RFC on React Native talking about the future of Yoga and what they want to it, how they want to adapt it to make it more like CSS. It may be part of it. Stay tuned. Thank you.